All right, I just realized, like obviously a minute ago, that I completely forgot to send out the invitations yesterday, like I should have. So let's give everyone a minute to get caught up here. I'm sure they're sitting there wondering what's going on. So now the invitation is arriving in their inboxes. And so what I'm going to do is go get the notes. Okay, that's good. And then we'll get started. All right. So first, let's go back to Moodle. And we're just basically going to pick it up where we left off last time. Oh, wait, actually. Oh, I didn't realize that would work. I thought I had to go to the main link. All right, very good. So log in. And of course, as you know, last time we'd started chapter 12, we were starting to make some progress in there. And also don't forget, chapter 12 is the last chapter of the semester. So we're getting pretty close to the end here. And first I've got to do this business. Yeah. All right. So now I can get in and open up Moodle. Kaliak, yes.
Yeah, Professor, I don't know if you did this or not, but did you ever release the grades for like the first midterms?
Oh, you know what? I put them into the grade book in Moodle. Did you not see yours?
Okay, I didn't check it. I didn't check that
Oh,
section.
see, now
Okay.
here's the thing though. I put them in there. There's a place where I can put grades, and I did, but I don't know how you see them on your side. Okay, that part I'm not familiar with because obviously my account is set up differently than yours. So if you go into your Moodle account, I think somewhere in there must be a place where you can see it. So that's why, because I put it in that grade book, and I was hoping that it would send you an email or do something to make it obvious that there was a grade in there. So now, having said that, if you go back in there and there's nothing there, just let me know, because that means there's something wrong with the grade book itself. But it should be there. Okay. Yeah. Anyone else? If you didn't see your grade, it's been in there for quite a while, as a matter of fact. And in fact, I'm still working on the current ones. And when I'm done with them, I'll start filling them in. And you can check periodically in your Moodle to see what your grade turned out to be, because obviously, you know, Thanksgiving is coming up and all. But I'm going to keep working on this stuff right up until the last minute. So I will have them done fairly soon. Before Thanksgiving, I'm pretty confident. And so, but that's how you'll find out. You can go look in your Moodle and it should be there. Now, of course, in the future, we'll be back into the classroom, so none of this will matter anymore. But as for right now, it should be invisible. And when you're done with your final exam, the same thing should happen. You should be able to see what your exam score was. And but then, of course, at some point, they'll give you your full semester letter grade as well. So hopefully you'll be able to see it fairly quickly after I've entered all the numbers. So, all right, anyway, so let's get this going. So hello to everyone, where I unfortunately, as you can tell, I forgot about the invitation until the last second. So I apologize for the screw up, but here we are. Yesterday was one of those days where morning to night, I just had stuff going on, and it was just crazy busy. So I just forgot. So anyway, we left off in chapter 12. Now there is a video that we can watch, but not just yet. We need to get some more material done before we're ready for it. There's actually 2 videos. So right now, let's just get back to 12. And of course, we're not meeting on Thursday, obviously. So when we get back, I think we have 2 full weeks left before the final exam. Now, of course, since this is an online class, there isn't really a final exam period as such. It just means that whatever day we finish the sample final rather, I'll post the actual final. And then you can hand it in by whenever we would have had our in-person exam, whatever day. I'll look that up. And so you'll have plenty of time to get it done. And since it's only based on 2 chapters, it shouldn't be too time consuming. In fact, if anything, it will probably be shorter than the first midterm, maybe about the same as the second one. So, all right, well, anyway, let's get back to this. So chapter 12, we did get started. And so we're going to carry on from there. And oh, let's get this open. All right. And let me just save it. Today's the 22nd. Now, I believe we left off with the weighted average or weighted mean. You recall first that in this section, we began by introducing, well, statistics itself, but we started by defining the distinction between the sample and a population. And we just want to make it clear that most of the time, it does not make sense to try to analyze an entire population because it just might take too long or be very expensive. So often what we do instead is we draw samples from that population and use the data contained in those samples to draw conclusions about the population. If the samples are chosen well, this shouldn't be a problem. So like, for example, if the US government is analyzing the ages of all the people who live in the country, they will pick random selections of people scattered across the whole country from different groups. And hopefully if they do this well, they should have a good reflection of the entire population. But if they did something, let's say instead by accident, they only chose people who are retired for some strange reason, then their results would be obviously thrown off because most of those people are actually quite old, and that would not reflect the entire country. So samples are good as long as we choose them carefully. That's the key detail, all right? We choose them carefully. They should give us a lot of useful information about the underlying population. Now, I think I mentioned this too as an example. You know, during an election season, you're constantly bombarded with polls. And you might see a poll that says, 42% of the population approves of this candidate. And you might think, well, they must have called up all the voters and asked them who they're planning on voting for, right? No. What you're seeing, those numbers are based on surprisingly small samples. In fact, for a poll about the entire country, let's say the president, some of those samples could be as few as a couple of thousand people. And so that group of 2,000 or 3,000 voters is supposed to represent all the voters in the entire country. So that seems a bit extreme, but again, as long as they were chosen in such a way that they reflect the overall population, the results should be reasonably good. Although you might know that in recent years, political polling has had a very terrible track record. It was getting to the point where people were starting to think of it as being very, very scientific. And now recently it started to really show that maybe it's not so scientific after all. But in other areas, polling or samples can do very, very well. But anyway, so what we also want to look at is several measures that help us understand the properties of either a sample or a population. And the first group of measures that we started to look at are the so-called measures of central tendency. Okay, so we have measures of central tendency. Then next we'll be looking at the so-called measures of dispersion. And then finally, we'll be looking at the measures of association. They all have different purposes. They all try to explain something different about a population or a sample. So the measures of central tendency are trying to help us find the center of a collection of data, whether it's a sample or a population. Okay, that's often useful information to have. And the three measures we want to focus on are the mean, median, and mode. And of course, the word mean is simply another word for average. In statistics, there are often multiple words that mean the same thing. So we have to be careful about that. So mean and average are the same idea. The median we'll get to next. And then finally, we'll briefly look at the mode. All right, so we briefly introduced the sample mean with this scary looking formula, which turned out not to be so scary because really all that it's saying is, if you want to know the mean of your sample, in the numerator, you simply add up all the elements in your sample. And in the denominator, you divide by the sample size. Okay, now the X's are the elements of the sample. Each one gets an index, 1, 2, 3, 4, up to N. And that way we can keep track of which one is which. And so this is very simply telling us, add up all the elements, divide by the size of your sample. This X with a little bar on top of it is meant to represent the mean of a sample. So that's what this is all about. Now, oh, and this fancy letter here, which is actually a Greek letter. I think I mentioned that. Right here. This is the so-called summation operator. It is used very heavily in statistics to tell us that we're supposed to add something up. And we did look at several examples of this. Now, one quick example for the sample mean was this case where we were looking at 3 different Starbucks in the Mall of America. It's such a big mall. There's probably a dozen Starbucks scattered around because it's literally several miles long, or at least, I guess I shouldn't say that. It's big. I'm not sure how many miles long it is, but it's enormous. And so there's naturally, if you suppose you're walking around in the Mall of America and you realize suddenly, hey, I could use a coffee. I just saw that Starbucks half a mile back. You may not want to walk all that way to get to that Starbucks. So that's why they very conveniently place them at strategic locations so that no matter where you are, you're not that far from a Starbucks. All right, they know what they're doing. These retailers, this is how they survive. They know how to get your attention, how to get you in the door, hopefully how to get you to buy things. And so a Starbucks out in the middle of there with all this wonderful coffee brewing away, you're going to notice it. Let's put it that way. But let's just say that you decided to do a little research here and you grab these 3 Starbucks and you write down the price of a cup of coffee at each one of them. And you notice, you would think they'd all be exactly the same, but if the mall is big enough and the stores are far enough apart, they may not necessarily have the same price, okay? Because remember, if you're walking around and you need coffee right now, you won't complain about paying $2.10, even though you know that there's another Starbucks half a mile away that's charging $2 a cup. It's not worth your while to walk half a mile for a dime. So you'll walk in there and say, whatever, it's $2.10, I'll pay for it. In fact, that's one of the reasons why, if you notice, gas stations don't all have exactly the same prices, because once you get there, imagine like you're looking at the price and you're saying, this is 10 cents more a gallon than I pay at my regular gas station. Most people are not going to just get up and leave and go to their other gas station, which could be a mile away, because it's not worth their while to save 10 cents a gallon. So these prices can be different, even though they're all Starbucks. Now, having said that, many chains like Starbucks and McDonald's, they may have rules about what the stores can charge, and they may decide that they should all have the same price, but it isn't necessarily true. So anyway, so here we are. So how do we calculate the average price of these Starbucks? Well, you notice how each Starbucks coffee price has an element associated with it, X1, X2, and X3. X1 is the first, or the price of a cup of coffee in the first Starbucks. X2 is the price in the second Starbucks, and X3 is the price in the third Starbucks. So up here you can see the average or sample mean is obtained by simply adding up the 3 prices, dividing by 3, and that works out to approximately $2.02. And that's all there is to it. Okay, so this could be potentially useful information for, let's say you're doing research about how much is being charged for these Starbucks, or imagine Starbucks itself is doing research and they want to figure out what is the best price to charge for their coffee. What they might want to do is walk around and look at how much their competitors are charging. And they might say, oh, our competitors are charging an average of $2.20. Maybe we should raise our prices. And this is how they would do it. They would grab a sample of their competitors and look at their prices and say, we should probably do whatever they're doing. All right, so anyway, the summation operator, we spend quite a bit of time practicing with the summation operator. And so let's skip ahead. And so now we just remember too, in this case, there's a separate formula for the population mean. Here's our sample mean over here. And you notice it's the same exact setup, except we've got 2 differences. Number 1, the X bar is replaced with the Greek letter mu, because we normally use Greek letters to represent population measures instead of the Roman alphabet. And number 2, we've got capital N instead of lowercase n. That way we know that this is a population size, not a sample size. it's important to keep them separate from each other because there are formulas and statistics where both values are needed, and we have to know which is which. So we don't need a separate example for this because it's exactly the same process, although it looks like I did create a separate example. This is the one where we had a small population of farms in Idaho. Okay, now farms, in this day and age, most farms are enormous. The days of the small farmer are pretty much over unless you're growing something very, very specialized. It's gotten to the point where the only way to make money in farming is to be big, because you need to spend a bundle of money on equipment, and it's not going to pay for itself unless you have a massive, massive farm. So big, wide open states like Idaho, where they grow a lot of potatoes, or Iowa, where they grow a lot of corn, this is where you're going to find most farms at this point in time. Now, 100 years ago, I mean, this whole area was all farms, and a lot of them were very small. In fact, even the Bronx at one point in the 19th century was primarily farmland. I mean, it's hard to believe now, but that's what was going on in all these areas in this where we live. Primarily, this was all farmland, and small stages. It started getting built up, and before you know it, the farms started creeping further upstate New York, and so now there's a lot of dairy farming done in upstate New York because there's plenty of room, but you're not going to see it down here, that's for sure. So anyway, these are the 6 farms in Idaho, and we want to know the population mean. So literally just add them up and divide by 6. So the average size is about 56.83 acres. All right. Now, the weighted average. This is a special case where we have a situation where some observations are more important than others, I guess you could say, or else they occur more frequently. Now, I think I mentioned the example of grades. For the most part, your GPAs are calculated as weighted averages, and the reason why that's necessary is because not all of your classes have the same number of credits. I mean, it's possible that they do, but for most people, some of your classes are worth more credits than others. Now, I don't know if you pay attention to that or not, but the next time you look at your grade transcript, you might want to look and see that some of your classes are worth more credits than others. For example, science and math classes tend to have more credits, especially if there's a lab involved with your science class, then there's going to be even more credits. I don't know enough about the other departments, like for example, any of the performing arts majors. I don't know how the credits are distributed there, but it's possible that even then that some of your classes are worth more credits than others. It really ultimately comes down to how many hours a week do you meet. But yeah, you should all be familiar with the number of credits that each of your classes are worth, because it does affect the way your average is calculated. So here's an example. Now, I mentioned here the Standard & Poor's 500, the S&P 500. This is the kind of thing that you will be paying attention to later on when you graduate and you have money to invest. All right, maybe not so much right now, but you most likely, some of your savings will be invested in the stock market. And one way to keep an eye on what's going on in the stock market is to look at the Standard & Poor's 500. It's an index, which means that a bunch of stocks, in this case 500, are averaged out to come up with a single number. And that number is very heavily watched in the financial markets, because when it goes up, that means usually the economy is doing very well. Now, the important part here is that the index is not a simple average where we take all 500 stock prices and divide by 500. Instead, the larger companies are given more weight in this average, and the smaller companies are given less weight. So when Apple price changes, it has a bigger impact on this index than when a smaller company does, because it represents a larger share of the economy, and that's the reason for this. So the S&P 500 is a weighted average. And by the way, while we're talking about it, just out of curiosity, in case you're really wondering about this and you really want to know more about what's going on in the financial markets, there's a wonderful website called cnbc.com, and they have everything going on here that you could possibly want to know. So there's the S&P 500. According to this, the current level is at 4,379.03. It's up $41.07 today, or about 0.87%. And you'll see next to it a couple of other stock indexes. Here's the Dow Jones Industrial Average, which you may have all heard about. That one's up a little bit today. The NASDAQ is the electronic index, where mainly technology companies trade here. It's up 104.88. And the Russell 2000 is the largest 2000 stocks in the economy. It's another index. So things are looking good today in the stock market. Now, I'll tell you why, because the chairman of the Federal Reserve System, which is the nation's central bank, who everybody likes in the financial markets, was given a new term. His term was up, and people were worried about who might be picked if he was replaced with somebody new. But instead, he got to keep, or he gets a second term, and that made the markets very, very happy because they trust him. And therefore, the markets went up. Okay. All right. Well, anyway, so now here's the formula for a weighted average. And what do you notice about it? In the numerator, we have two things being multiplied together. Each X, or each element in our sample, has its own weight, which you'll see in the example that's coming up. In the denominator, we just have weights. All right. So what are you actually doing here? In the numerator, for each X, you multiply it by its own weight, and you add them up. In the denominator, you just add up the weights. And when you're done, you'll have your sample mean, sample weighted mean. Now, it looks scary and mysterious, but when we do an example, you'll realize it's not that difficult at all. Also, I'd like to point out that just like before, we have a separate formula for the population mean, and it's only slightly different. I've replaced the X bar with a mu again, and the capital N is now replacing the lowercase n. Now, here's an example. This is kind of an interesting example. Suppose there's a lottery, but it's not the New York State lottery. It's not a gigantic lottery. It's a small lottery. It has a prize of $1,000. It has 10 prizes of $500 and 100 prizes of $10 each. What is the average prize received by a lottery winner? Now, you might be tempted to say, well, why don't we just add up 1,000 and 510 and then divide by 3? It seems like the right way to do it, but that would be wrong, because we have a lot of $10 prizes and only $1,000 prize. And so therefore, we're not going to simply add them up and divide by 3. We're going to create or calculate a weighted average. The weights will reflect how many prizes there are of each value. So if you look at these, I put together a little chart. The 3 prizes will be the X's, and the number of prizes will be the weights. Okay, the weights are simply the number of prizes. Now we're going to take this information and calculate the weighted average of the prize in this lottery. All right. Now, so here we go. So on the next slide, I've got the actual formula with all the numbers plugged in, and I've written out what the formulas represent. So in other words, you see what I've done here. Actually, you know what? Let me see if I can copy. Might be able to sneak in that little chart. I'd like to have it there. Hold on one second. It's easier if everything's on one slide, I think. Just about squeeze it in. Oh, well, that worked out rather well. I wasn't positive I could do that. I just bought this program called Snagit, which lets you take pictures. This is a PC, by the way, which lets you take pictures. I know the Mac has its own capabilities, But all right, that's good. So you can actually see, now look what's happening here. We've got in the numerator, each weight times each X, okay, 1 times 1,000 plus 10 times 500 plus 100 times 10. And in the numerator, by the way, that adds up to 7,000. And the denominator, we're just adding up the weights, 1 plus 10 plus 100. So when you take and by the way, that adds up to 111. I've got it up here. So 7,000 over 111 is 6,306. So the average price is 6,306. Now you're probably wondering, well, wait a minute, look how big those prizes are. How can the average be so small? Well, the reason for that is because there's so many $10 prizes and so few of the larger prizes that the average is going to be much closer to 10 than either 500 or 1,000. Okay. And that's the final answer. 6,306 is the average prize. Now, in the next example, I've decided to go ahead and show you a GPA example because I know this is important to you. Imagine that this is your schedule. All right, let me give you a minute to catch up. And then I'm going to show you this fictional schedule. And we've got 4 classes with 4 grades and 4 values of the credits. And we're going to see how the average is calculated. All right, here we go. Now imagine this is your schedule. You've got pre-calc, English 101, history of Western civilization, and physics. Those are your letter grades. These are the equivalent numerical grades. For example, an A- is worth 3.7 points. A C+ is 2.3, and these are the credits. Now, as you know, like I said before, often math classes and science classes have more credits than the other classes. Like English and history and sociology and philosophy. The social sciences and English tend to have 3 credits. And now, how do we calculate your GPA though? Now, you might be tempted again, if you didn't know any better, you would add up these 4. Of course, you do know better now, and divide by 4. But you can't do that because the pre-calc grade and the physics grade are worth more than the English and history, or at least worth more in your GPA. I don't mean they're necessarily better classes, but they're weighted more heavily in your GPA is what I should say. So here's what I did. The same chart, now you can see what I've done is I've introduced X and W. Oops, forgot about that. And so this way you can see very clearly the grades. And this thing is really, see sometimes this doesn't work. Theoretically, it's supposed to let me create a font there, change the font. Oh. Oh, there we go. It's just being stubborn. Okay. So anyway, yeah, you've got your 4 X's and your 4 weights. The weights are the credits and the X's are the actual GPAs, the numerical grades. So now when it comes time to calculating your average, we're going to use the same formula. And I've repeated the chart here so you can see what's going on. You've got all your W's. And down here, you've got just W's. And that gives me 46 over 14, 3.29. That's your GPA. And by the way, if you just added them up and divided by 4, I'm going to do this right now on my calculator. You would have only gotten 3.25. So you would have been cheating yourself out of some 4 points there. So yes, you have to take into account the fact that the physics and the pre-calc have more credits when you calculate your GPA. So that mystery has been resolved. Now, when you look at your transcripts and you say, hey, how did they come up with these numbers? Now you know. Although I guess it's not a transcript anymore, is it? They used to send you a document in the mail like long after the semester was over, and it would just have all your grades listed. I guess now everything's online, huh? Yeah, well, that's cool. That way you find out about it pretty quickly. All right. So that's all we need to say about the mean. Now, what about the median? Now, remember, we had three measures of central tendency to cover. The mean, the median is second. Now, what exactly is the median? Median is different. We're trying to find the middle of the data, but in a different way. We're looking for a value that splits the data in half. In other words, half the elements are less than the median and half are greater. Divides the sample right down the middle. So imagine, well, we'll see some examples. Let me show you an example of this. Or think about this. What if you were told, let's say you got a score in your exam of 70, and you're told that that's the median score. That means half the people in the class did worse than you and half did better. That's what it means. You're right smack in the middle. Okay, now what if I told you that the median age of all Americans is 28? That means half are younger than that and half are older. All right, now I don't know if that's the actual median or not, but if it were, that's what it would mean. All right, so now we're going to actually calculate it. I'm going to show you how this is actually obtained. It's a little bit different than what we're used to seeing here. So now we're going to return to an example that we had earlier. These are the 5 elements of our sample now. And this time, instead of the mean, remember the mean was 2, by the way, we're looking for the median. Now, what we're going to do first, and this was never necessary before, is we're going to sort the numbers from the lowest to the highest elements. Okay. So if you do that, now luckily these are integers, so it's easy. If you sort them out, they're going to look like this. -1, 1, 2, 3, 5. Now, remember, we're looking for the element in the middle. Divides the data in half. So you can see on the next slide that clearly must be the 2. 2 are below, 2 are above. This is the center of the data. And that's it. That's all you had to do. Now, there's just one complication, though. When we have an odd number of values in our sample or population, it's easy to do this. You're just looking for the element that's right in the middle. What about cases where we have an even number of elements? Ooh, that's going to be a little trickier. So let me show you an example of this. All right, so here 2 is the median. But now what about this case? This is a different sample. We have 6 elements. 6 is clearly an even number. And here's what's going to happen now. When we sort them out, the sorted elements are going to be 0, 1, 2, 3, 4, and 6. So now the question is, where's the center? Which element is in the middle? Oh no, we're stuck. Well, there's a compromise that we can do. Why don't we take the 2 in the middle and average them out? There you go. Now, would you agree that 2.5, half the elements, let me write them here again, are below 2.5 and half are above 2.5. So even though 2.5 is not an element of the sample, we can still treat it as the median because it does in fact divide the data right down the middle. So anytime we have an even number of values, this is exactly what we're going to do. And let me show you in the next slide. I've done it with the colors. 2 and 3 are the two in the center. We average them out and we find a number such that half are below and half are above. So there's two cases then. The odd number of values, we just find the element in the middle. With an even number, we split them up. We average the two in the middle and we have two halves that are half are below and half are above the median. Now, you might have noticed that there's no formula here. It's just a process. Okay, it isn't always possible to reduce a set of calculations to an equation. This is one of those. Okay, instead, it's understood that you're going to follow a series of steps until you find your median. Okay, what are those steps? Sort the data, find the data in the middle. In the case of the odd number of values, there is already one in the middle. With an even number, you average the two in the middle. So in other words, but in general, this is what you're doing. You sort the data, find what's in the middle. There's no formula that can express this. The other thing I want to point out is because there's no formula, the sample and population median are treated in exactly the same way. We do not have to make a distinction between them. In both cases, we do the exact same thing. Okay, now you're probably asking yourself right about this time, when would I use the median and when would I use the mean? They're clearly both measures of central tendency. They're calculated differently, but they're both measures of central tendency. I want to know when I should use each one. Well, the answer to that question depends on whether or not our data contains something called outliers. What exactly is an outlier? An outlier is a data point or element which is either much smaller or much larger than the rest of the sample or the population. It's a number that sticks out like a sore thumb because it's so much bigger or smaller than the rest. And we'll see in a few minutes, but I'll just tell you right now that when we have outliers, I might as well write it right here. Use when our data contains outliers. And again, we'll see an example of this in a minute. But this is just telling you where we're going. And then the mean should be used when our data does not contain outliers. Okay, so that's the rule of thumb right there. If there are outliers, we're better off using the median. And that's because the mean is distorted by outliers, as we'll see. All right, so let me show you a quick example of an outlier. You probably have experienced this. Imagine that we're interested in looking at the heights of the students in our classroom. And there's a basketball player in the class, and he's 7'3". The rest of us are much, much smaller. His height could be considered to be an outlier because he's so much taller than everyone else. Okay, that could be thought of as an outlier. You got, imagine the heights are like 5'9", 6 foot, 6 foot, 5'9", 5'8", 7'3". So that basketball player's height could be thought of as an outlier. All right, or here's another one. I don't know if you're aware of this or not, but SUNY has this program where if you are above a certain age, I think it's 65, you can get permission to take classes at the school and pay essentially no money. I mean, very, very, very little money. It's essentially free. So imagine yourself retiring from a long, hard career in something, and you say to yourself, you know, I always wanted to study poetry. And you go to Purchase and say, hey, I'm going to sign up for this poetry class, and it's almost free. And this way I can enjoy my retirement and yet still not spend all my time having fun. I want to learn. I want to keep learning. I don't care how old I am. I want to keep learning. So imagine that in your class, you're in a poetry class, and there's that one person who is taking the class for the fun of it. And she's 75 years old. Okay. So all the other students in the class are probably between 18 and 21. And this one retiree who just shows up because she loves poetry is 75. So her age would be an outlier because she's significantly older than the rest of the people in the class. All right, so that could be thought of as an outlier. Now, the reason why, give you a hint as to where this is going. Suppose somebody came in there and said, I wonder what the average age is of all the classes at SUNY Purchase. What's going to happen in this class? You add up all the ages, including the retired person, and calculate the average. And what if it comes out to be 24? Well, you can see the problem. Technically, that is correct. The average age in that room is 24, but only because that one person is so much older than the rest. So the 24 would be a little bit deceiving, given that almost everyone in that room is, let's say, 19 or 20, yet there's one person who's 75. So the mean in that case is going to be very questionable as to its value. So that's when you might think about using the median instead of the mean, because then it would be a much more meaningful measure. Now, like here's an example, a numerical example. We've got a group of observations in our sample. And by the way, have you ever had a class with somebody who's retired? I have had a few. And sometimes it works out for them, sometimes it doesn't. I mean, if there's a lot of math involved, it's probably not what they were looking for. But I admire people who continue to learn even after they're retired. I mean, come on. You know, it's you can only spend so much time at the beach, right? I like that idea. In fact, I'll probably do this myself when I get to that point. Why not? I'll come back and take all the classes I never had time to take before. So you might see me, no, it's too soon, but maybe your children will see me in these classes. Anyway, so look at this one. 2, 3, 1, 3, 5, and all of a sudden 100. Where did that come from? Well, I think it's pretty obvious that that's an outlier. Now, oh, by the way, there's another great example. Maybe let me throw this one in here too, because this is something you see in all the time in practice. Suppose that in your town, the average house price is, I don't know, $400,000. One day, Bill Gates, for God only knows why, builds a mansion in your neighborhood worth $50 million. I don't know. Clearly, this is an outlier. The mean value of houses in the neighborhood will rise substantially, but it is only due to this one house. You can see the mean is not going to be a good choice here when you have this one enormous outlier. Okay. Now, why did I mention that one? Because when the government calculates incomes in the United States, you know that a lot of people make similar money, but there's a few people who are just crazy, crazy rich, like Jeff Bezos and Elon Musk. So because of those super rich people being part of the population, the government will use the median to calculate or to represent incomes rather than the mean, because those are outliers and they will cause the numbers to look higher than they really are. But anyway, so in this case, what we're going to do is calculate the average. Now, you see the average in this group, I mean, 2, 3, 1, 3, 5, 100 is 19. Now, I don't think that's a terribly meaningful measure of central tendency because as you can see, let me just quickly copy this into here so you can see it better. Just want a quick reminder there. We added these up. The average is 19, but guess what? 19 is larger than all the observations except one. So I think you'll agree that in this case, 19 is not a good measure of the center of the data. It's very deceiving. Let's put it that way. But if I calculate the median, oh, now that's a different matter. Because look what happens now. I sort them out. And based on the rule we had earlier, there's 6 values. So I have to average out the 2 in the middle. And you'll see that the median is 3. Now, I think you'll agree that 3 is a much more meaningful measure of the center of this data than 19, which is way out here. Okay, 19 doesn't really tell us a whole lot, but the 3 is a very useful measure of the center of this data. Not only that, but guess what? Look what happens. Even if this 100 was 100 million, it does not affect the median. So the beauty of the median is that it is not being distorted by outliers, whereas the mean is. So that's why when we have outliers, often we prefer to use the median rather than the mean. But most of the time, the mean is the best choice because, first of all, it's intuitively more clear to people what it means. And secondly, it's easier to calculate. So much of the time, we prefer the mean, but when there are outliers, the median is suddenly the best choice. Okay, and then finally, now the mode is a very interesting case. The mode is not really as important as the other two. I'll tell you when the mode is very useful. The mode is not as useful as the mean or median or numerical data. But on the other hand, it can, unlike the mean or median though, the mode can be applied to non-numeric data, such as colors, flavors, styles, sizes, etc. Well, sizes technically are numbers, but they're not, they can't be directly compared to each other. So let's just stick with this. All right, so the mode is kind of not the most important, but if we're dealing with something that's not numerical, like colors or styles or something, or regions, whatever, then the mode is more useful. So how does this work? Well, first of all, let's go back to our sample. And just like with the median, we're going to have to sort them out. Okay, that's the first step. Now, of course, these are integers. Like I said, it's easy to sort. 1, 2, 3, 3, 5, 6. What are we looking for, though? We're looking for the element that occurs the most frequently. That's all there is to it. And because there's more 3s than anything else, our conclusion is that the mode is 3. All right. Well, that was easy, but there's a couple of quirky things about this that we have to know. What about this case? Suppose that the sorted elements of a sample are 1, 2, 4, 5, 7, 8, 9, 10. In this case, there is no mode since no values are repeated. So in other words, there doesn't have to be a mode. Now that's unusual. You don't see that with the mean and the median, do you? No. There's guaranteed to be a mean or a median for every sample or population. And then here's another case that I wanted you to see. Suppose that a sorted sample consists of the values 1, 2, 2, 2, 3, 4, 4, 4, 5, 6, 7. Well, I just wanted to make it interesting here. What numbers are repeated? Well, look at this. There are more 2s and 4s than any other value. The mode is therefore both 2 and 4. Wow, it can be 2. There can be 2 different modes. That's, again, something you do not see with the mean or the median. So that's one of the really strange things about modes. First of all, there doesn't have to be a mode. And secondly, there can actually be 2, and there can be more than 2. Okay, there's in principle no limit to how many modes we can have. Wow, now that's very bizarre. And you can see this is one of the reasons why we tend to shy away from the mode, because it's just maybe not so useful. Let's try this one. So here, the modes are 2, 3, and 4. There's 3 modes because you've got 2 2s, 2 3s, and 2 4s, and none of the others are repeated. 3 modes. Wow. That's wild. Interesting. Now, there are names for these cases. A sample or a population that has a single mode has its own name. And all right, well, I'm giving you a second to catch up. So here you can see the reason why there's 2, 3, and 4 is because those are the only ones that are duplicated. All right, here we go. A sample or a population with a single mode is unimodal. A sample or a population with 2 modes is bimodal. And there's another one too. A sample or a population with 3 modes, as you can probably guess, is said to be trimodal. I don't think there's any names for the rest of them. You don't really see this very often. Okay. So, oh, one more thing. As with the median, let me just add this. There is no formula for computing the mode. In addition, okay, that's better. So in other words, just like the median, we don't really need to distinguish between the sample and a population because the procedure is exactly the same. All right. Now, those are the 3 measures of central tendency, but we have one more topic to look at here. We can gain insights into a sample or a population by looking at the relationship between the mean, the median, and the mode. So in other words, for certain applications, we need to look at all three of them. And here's what I'm going to show you, some graphs, some special graphs that help us understand what's going on in our sample or our population. You may have seen these before. In fact, why don't I give you a quick detour here. I'll tell you what, let's sneak into Excel here for a minute. What I'd like to do, let's say I have data. It could be for anything. Let's say that I observe the temperature, the daily temperature in New York during the winter. All right, so I take 20 temperatures, and then I'm going to organize them into groups. Actually, I don't even need to do this. I'll tell you why. Excel can do this for us. So the range here, I just need to do one thing here. I'm going to ask Excel to tell me what are the smallest, since I just made these numbers up, I'm going to ask it for the smallest and the largest. All right, so all the temperatures are between 16 and 40. All right, so here's what we'll do. About 10 to 20, 20 to 30. Well, no, let's do it this way. 10 to 15, 15 to 20, 20 to 25, 25 to 30, 30 to 35, 35 to 40. All right, so now Excel has a capability built into it. We're creating a special kind of graph. So if you have the PC version of Excel, you go to data analysis, histogram. Now what it's offering to do is not so much draw the graph for you, but organize it for you. And you look at it and say, well, what's the big, oh boy, that's not what I wanted. Yes, it is. This is just 40. Okay, so what I'm going to do now is create a special type of graph. And it's a special type of graph. And let's see, I can clean this up a little bit. Oh, see, it disobeyed me. Why did it do that? That's very strange. Oh, I see what it's doing. Okay. That's what I wanted. Okay. All right. So anyway, what am I trying to do here? I'm trying to see, that's strange because now it's not giving me the right numbers. Oh boy. All right, hold on. I don't want to waste too much more time with this. Okay, now it looks, oh, but now we lost these. What's wrong with this thing? All right, I think we finally convinced it to work properly. All right, so what am I trying to show you here? It's a special type of bar chart. And basically the way it works is that you've got ranges of values across the horizontal axis. The vertical axis represents frequencies. How often did this happen? And this type of graph is often referred to as a histogram. It basically comes from, it's a combination of Greek words. It basically means you have these vertical bars on the graph. So the heights of these bars tell me how many times the temperature fell into that range. Okay. In fact, but anyway, so you get the point. You see more times. We had somewhere between 35 and 40 degrees. You know what? Let me do this real fast. Oh crap. Oh, oh God. There we go. Just so you can really and truly see what's going on here. No, something's not right. This one should have been 35 through 40. Oh my God. Now, all right. We don't have time to play games with this stupid thing. I don't know what its problem is, but anyway, you get the idea. So that's a histogram. So we can often gather a lot of insights about a set of data with one of these histograms. And so what we're looking for is 3 different situations and that might pop up with our data. And we'll see what these are supposed to represent. The data might fall into one of these 3 categories. It can be negatively skewed, it can be symmetrical, or it can be positively skewed. So when you see the pictures, you'll understand pretty quickly what these represent and how they're determined by the relationship between the mean, median, and mode. Now, not all data falls into these categories, but it's important to know if it does. All right, so, sorry. So what I'm going to do is show you what does it mean. How do we define each of these, number one, and then what does it look like when this is true of our data? So the negatively skewed case happens when the mean is smaller than the median, which is in turn smaller than the mode. So let's see what this looks like. Now, the data we're about to see are stock prices, or stock returns, actually. And you can see, well, this is an unfortunate outcome because if you notice, the numbers on the left are all losses. All right, starting at about here, these are all losses. So these are losses and these are gains. So are you happy if you own this portfolio of stocks? No, because your losses occurred more frequently than your gains. And so whenever the pattern of the bars looks like this, the data is said to be negatively skewed. So it's kind of like a big mountain with a long left peak. I mean, imagine down here, it takes a long time to climb up the mountain and not so much time to climb down the mountain, going from left to right. So remember, this is the case where we have mean less than median less than mode. So we don't want this for our stocks. For other situations, maybe that would be okay, but not so much here. Now, the second case, which is called symmetrical, it means that all three of these are equal to each other. So the word symmetrical means there's a balance. All right, so we're going to see exactly what that means in a second. All right, so are you ready to see this graph? When you see it, you're going to say, wow, that looks nice. Because what is happening here is that the two sides are perfectly balanced. The gains, the losses are exactly matched by the gains. It's as if there's a mirror down the center here. The left and the right-hand sides are mirror images of each other. And that's because the mean equals the median, which in turn equals the mode. Okay, and then finally, there's one final case that we might encounter, which we can identify with our mean, median, and mode. So you probably can figure out which one we haven't done yet. How about this one? How about when it's the mean that's the largest, larger than the median, which is in turn greater than the mode? Then we say the data are positively skewed. And when you see this graph, you'll realize, yes, this is what I want with my stocks. Absolutely. All right, are we ready? Yes. Okay, here we go. So this is the happy case because you can see the gains far outnumber the losses. And so remember, this is the case where the mean exceeds the median, which in turn exceeds the mode. All right. So that's all we need to say about measures of central tendency. The next group of measures, the measures of dispersion, are a little bit more complicated. But we are going to now check out a video which ties together very nicely what we've just learned about mean, median, and mode. We'll have to save dispersion for after the break because it's the kind of thing you want to start at the beginning of the class, not just start to introduce it and then have to do it all over again. So why don't we watch the video? And so hold on, let me go get it. It's a nice overview of mean, median, and mode. Hold on.
Right.
Hold on.
It's Ryan Reynolds.
All right, I'm going to send that right over to you. And let's check it out.
I know Halloween was a few weeks ago, but right now, the big wireless company.
Hi, I'm Adrienne Hill, and welcome to Crash Course Statistics. In the last video, we tried to make sense of ginormous numbers and teeny tiny numbers. Today, we're going to talk about less showing numbers, the numbers stuck in the middle, the averages, the medians, the modes. They may not seem as mind-blowing or all that flashy, but turns out they're really, really important. Those middle numbers are often the ones that get all the press attention, get tossed back and forth in political debate, and they give us this little fun bit of trivia. What's the average or mean number of feet people have? It's not 2. Turns out the average number of feet people have is a little less than 2, because the average takes into account the small number of people out there with fewer than 2 feet. So if you have 2 feet, you have more than the average number of feet. And with that, let's get into measures of central tendency and why they're useful. If your boss asks you for a report on this quarter's sales numbers, but is rushing to a meeting and only has time to listen to one piece of information about that data, that piece of information you give her should probably be a measure of central tendency. The center of a bunch of data points is usually a good example or summary of the type of data we can expect from the group as a whole. One common measure of the middle is the mean. You've likely heard it called the average, though all of these measures are sometimes called averages. Some people call the mean the expectation of a set of data. The mean or average takes the sum of all the numbers in a data set and divides by the number of data points. So if 10 pregnant dogs give birth to 50 total puppies, the average litter size is 5 puppies. Each data point, in this case, each litter of puppies, contributes equally to the calculation. Aww. Here's another example. Say you have $10 and your best friend has $20. The mean amount of cash you two have is $15. 10 plus 20 divided by 2. But saying that the mean is $15 doesn't mean you each can buy that $12 BFF necklace that you've been eyeing. You know, the one with half a heart that fits together? You personally only have $10 in your pocket. The average of a set of data points tells us something about the data as a whole, but it doesn't tell us about individual data points. The mean is good at measuring things that are relatively normally distributed. Normal means a distribution of data that has roughly the same amount of data on either side of the middle and has its most common values right around the middle of the data. Data that are distributed normally have a symmetrical bell shape that you've probably seen before. A distribution shows us how often each value occurs in our data set, which is known as their frequency. Imagine you're trying to impress your new college dorm mates by guessing how many times they've each seen Harry Potter and the Sorcerer's Stone. Your mom is in the entertainment industry, and you overheard at her last dinner party that 18-year-olds on average had seen the movie 5 times each. That's a lot of Quidditch. So you should guess your new friends have seen the movie 5 times each, unless you can clearly see Slytherin tattoos. You won't be right each time, but it's your best guess. It might not be the best way to impress them, though. It's really not a great party trick. Sometimes the mean is misleading. For instance, life expectancy in the Middle Ages. As we explored in Crash Course World History, there was an incredibly high rate of infant mortality in the days before modern medicine. But the people who made it to adulthood lived relatively long lives. Because of the high rate of infant and child mortality, the average life expectancy was about 30 years. But things weren't nearly as dire as all that. Not if you actually made it to 30. In the 13th century, a male who lived to 30 was likely to make it to his 50s. To give unusually large or small values, also called outliers, less influence on our measure of where the center of our data is, we can use the median. Unlike the mean, the median doesn't use the value of every data point in its calculation. The median is the middle number if we lined up our data from smallest to largest. For example, if you have 2 cats, Jillian has 1 cat, and Eric has 3 cats, the median number of cats in your little cat-loving group would be 2. When we put the number of cats in order from the least to the most cats, 2 is in the middle. But what if there's no middle number? You invite Will to join your cat group. He has an impressive, or is it excessive, total of 14 cats. Now there are 4 cat owners. There is no one middle number. Both 2 and 3 are in the middle. In this case, there are differing opinions on how to calculate the median, but most often we take the mean of the two middle numbers. So our median would be 2.5 cats. Meow, meow, me. Let's go to the thought bubble. Imagine 10 artists have been working for years together to come up with a new, fresh way to tie macrame knots. The standard square knot just wasn't inspiring them the way it used to. And finally, they do. Voila, that abracadabra Doolittle knot. So these 10 artists go out to celebrate, and they go to a relatively modestly priced restaurant because macrame artists just don't make all that much money. Each of them pulls in about $20,000 a year. So the average or mean income around the table is $20,000, and the median income is also $20,000. Now let's imagine that Elon Musk gets wind of this macrame milestone. Turns out he's a huge macrame fan himself. Beauty in design. He couldn't miss up a chance to celebrate, so he decides to show up at the restaurant. Musk's total annual compensation, including his salary and stock options, is reportedly in the neighborhood of $100 million. As soon as Musk walks in the door, the average income in the room skyrockets to a little over $9 million. But nobody else in the room is actually richer. Nobody feels any richer. The median income of the macrame artist and Musk is still $20,000 because most of our group is still making $20,000. And this isn't just the stuff of our make-believe macrame world. It happens in real life too. The average is distorted by outliers. Thanks, Thought Bubble. All right, now say there's a controversial book on Amazon called Pineapple Belongs on Pizza with 400 reviews, 200 5-star reviews, and 200 1-star reviews. The mean number of stars given was 3, but no one in our sample actually gave the book 3 stars, just like no one could actually have the median of 2.5 cats. In both of these situations, it can be useful to look at the mode. The word mode comes from the Latin word modus, which means manner, fashion, or style, and gives us the French expression a la mode, meaning fashionable. Just like the most popular and fashionable trends, the mode is the most popular value. But we don't mean popular like Despacito popular. When we refer to the mode of our data, we mean the value that appears most in our data set. For our Amazon reviews of Pineapple Belongs on Pizza, the modes are both 5 and 1, which gives us a better understanding of how people feel about the book. These reviews are called bimodal because there are 2 values that are most common. Bimodal data is an example of multimodal data, which has many values that are similarly common. Usually multimodal data results from 2 or more underlying groups all being measured together. In the case of our book, the 2 groups were the love it 5-star group and the 1-star group. Or for another example, if we made a graph of the times customers went in and out, we probably see 2 peaks because there's 2 groups of people, one around lunchtime and one around dinner time. The mode is useful here because it's an actual value that occurs in our data set, unlike the median and mean, which can give us numbers that wouldn't actually occur and don't describe our data very well. The mean time people come into in and out may very well be 3:30 p.m., but that doesn't suggest you should expect an overflowing restaurant in the middle of the afternoon. You should be able to get your animal style burger and fries without too much of a wait. The mode is most useful when you have a relatively large sample so that you have a large number of the popular values. One other benefit of the mode is that it can be used with data that isn't numeric. Like if I ask everyone their favorite color, I could have a mode of blue. There's no such thing as a mean or average favorite color. The relationship between the mean, median, and mode can tell us a lot about the distribution of the data. In a normal distribution that we mentioned earlier, they're all the same. We know that the middle value of the data, the median, is also the most common, the mode, and is the peak of the distribution. The fact that the median and mean are the same tells us the distribution is symmetric, that there's equal amount of data on either side of the median and equal amounts on either side of the mean. Statisticians say the normal distribution has 0 skew since the mean and median are the same. When the mean and median are different, a distribution is skewed, which is a way of saying that there are some unusually extreme values on one side of our distribution, either large or small in our data set. With a skewed distribution, the mode will be the highest point on the distribution, and the median will stay in the middle, but the mean will be pulled toward the unusual values. So if the mean is a lot higher than the median and mode, that tells you there's a value or values that are relatively large in your data set. And a mean that's a lot lower than your median and mode tells you there's a value or values that are relatively small in your data set. Let's go to the news desk. The average income of a US family grew 4% between 2010 and 2013. Those average paychecks expanded from $84,000 to over $87,000. But not everyone is cheering. The median income fell 5% during those same years. Median family income dropped from $49,000 to just over $46,500. This really happened back in the years after the financial crisis. The mean income rose at the same time the median income fell. That's because families at the top of the income distribution were making more money and pushing the mean up, while many other families were making less. And even though unscrupulous politicians could accurately claim average incomes are rising and pat themselves on the back, it would be misleading. For most Americans during that stretch, incomes were flat or falling. This points to another really important point about statistics, a point we'll come back to time and time again in the series. Statistics can be simultaneously true and deceptive, and an important part of statistics is understanding which questions you're trying to answer and whether or not the information you have is answering those questions. Statistics can help us make decisions, but we've all got to use our common sense and a little skepticism. Thanks for watching. I'll see you next time. Crash Course Statistics is filmed in the Chad and Stacy Imigholt studio.
All right, so I guess we're done. And I will see you all next Monday. So I hope you have a great Thanksgiving. Okay. All right, bye everyone.